In recent years, you may have heard of the term machine learning, and you may have wondered what that is. Machine learning is the method programmers use to teach computers to do things that we can't explicitly program them to do. You see, computers are math machines, that's all they are. Behind the web browser you're watching this video on, and behind the operating system this browser runs on, all your computer is really doing is math and manipulating data. A talented programmer can make a computer do almost anything that can be reduced into simple logic and math. That's what coding is. But what if you want your computer to do something more abstract, say recognize a face or drive a car? These problems cannot be reduced into pure logic and math, at least not in the traditional coding sense. How would you describe a human face to a computer? Sure, it has two eyes, a nose, and a mouth, but that only kicks the problem further down the road. What differentiates a human eye from a dog's eye? How do you even describe an eye with math? The answer is that you can't. It's simply too abstract and there are too many variables to strictly define. This is where machine learning comes in. Inspired by the real world, programmers can create virtual neural networks that closely mimic what the neurons in your very brain are doing. Of course, your brain contains trillions of neurons, which is simply not possible to simulate with today's computers, so the virtual neural networks are many orders of magnitude smaller. Still, these small neural networks can almost magically do things that we could never explicitly program a computer to do. A neural network by itself cannot do anything. It needs to be trained first, or learn. It does this by running thousands or even millions of tests, each time getting incrementally better until it eventually performs a desired task. That's the basic gist of it, but we can dive a little deeper. There are three main types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the network gets a specific input and is expected to give a specific output. This could be used for our facial recognition example. Show a neural network 10,000 pictures of faces and dogs and it will eventually become pretty good at telling one from another. Much like supervised learning, we have reinforcement learning. Here, the algorithm is given feedback on its previous experiences. However, this feedback comes in the forms of rewards and punishments based on its performance. It is again kind of inspired by the real world. You can think of it as evolution, where the neural networks that perform poorly go extinct, and those that perform well live to prosper. Survival of the fittest, if you will. Finally, we have unsupervised learning. Here, the neural networks will not be given any explicit feedback. The goal is more to uncover patterns in the training data. This type of learning can be utilized in situations where the training data can be automatically generated without much human effort. What's common for every type of machine learning is data. They all need data. Lots of data. Big data. Big data is a relatively new term that comes from the fact that we today collect more data than at any point in human history. Every place you go, website you visit, or item you purchase is recorded, stored, and probably eventually analyzed by a machine learning algorithm. Companies use these extreme amounts of data to train their algorithms so they become more efficient and accurate. Big data is characterized by 5 dimensions: volume, the sheer quantity of data; velocity, the speed of data generation; variety, the type or format of data; veracity, the reliability and trustworthiness of the data; and value, how insightful the data is. These are the keys to improving machine learning algorithms, but in order to harness the full potential of big data, there are some obstacles that need to be overcome. The hardest part about training a computer is not designing the neural network. It's actually pre-processing the data into a format that's useful for a machine learning algorithm. This pre-processing aims to fix issues such as data inconsistencies, redundancy, noise, imbalance, and more. Pre-processing is the hard part because it actually requires manual human labor. Before a machine learning algorithm can train on 10,000 images of human faces and dogs, there must first have been a human to label the images correctly. How else would the algorithm know it was guessing correctly? When working with big data, it is simply not possible to manually pre-process even a fraction of all the data. Furthermore, the sheer amount of data makes many traditional machine learning techniques obsolete, because they aren't efficient enough to cope with the scale. So, computer scientists have to come up with smart solutions. There have been studies on how to parallelize many traditional machine learning algorithms to improve performance. Parallelization means spreading the workload over multiple computer cores so they can work in parallel at the same time. Researchers are taking this concept even further with distributed machine learning, where the learning process is spread over multiple different computers. Obviously, the more computers you have crunching numbers, the better, but this is an extremely hard task, and more research is still needed on the topic in order for machine learning to fully utilize the potential of big data. You see, with traditional machine learning, typical performance metrics would include things like accuracy and error rate, but when applying big data to machine learning, new metrics are needed in order to assess the performance of an algorithm. Here, scalability is the all-deciding metric. We're looking at data I/O performance, fault tolerance, memory usage, and the likes. Problematically, current systems that scale well will often have worse performances than systems that don't. There are trade-offs between the two, and researchers aim to strike a nice balance. More problems with combining machine learning and big data include how to protect sensitive user information. One real-world use case for machine learning is that it could learn from medical data to potentially discover disease before a doctor could. The problem is that this data could be highly sensitive. How do we allow machine learning algorithms to train on data without risking leaking sensitive information? Making machine learning accessible to the general public is another one. Right now, most people have no clue what machine learning is, let alone how it works. It would be beneficial if non-experts could interact with machine learning in order to use machine learning's capabilities in other areas. There are many more research issues that are still open. With volume, we have how do we clean and compress big data. With velocity, we have how do we optimize workflow management and working with real-time online learning for streaming data. With veracity, we have how do we assess data veracity and how can we learn unreliable or even contradicting data. So to cap things off, in order to unlock the full potential of big data, to uncover the hidden knowledge and insights that may hide, researchers must develop new and sophisticated systems in order to utilize machine learning and big data together. Doing this would spur scientific breakthroughs that would change the world for better in countless ways. Self-driving cars are quickly becoming significantly better and safer than human drivers, reducing motor vehicle fatalities and reducing congestion on roads. Machine learning will also be used in the medicinal industry to diagnose diseases better than real doctors ever could. The possibilities are endless, and it's almost certain that new use cases will arise that we cannot even imagine yet.